Let's bring together everything that we've talked about in this fairly lengthy discussion of point estimation and sampling distribution. Let's go back to the very basic essence of this transition we've made from the probability world to the statistics world, and that is that the whole reason why we do statistics is for statistical inference, and that is that we are going to make decisions about populations based upon a random sample. That's the general overall kind of thing, and that's what we're just beginning to get into. And what we're really going to do here is, in this very specific module, is that we're going to use the sample statistics that we get from a random sample as point estimates of parameters of interest. So, for instance, we talked about the method of moments, and that was all about the expected value of the nth moment and setting that equal to the observed value of that moment, and how that emphasizes the body of the distribution. It may not be all that good, especially if we're interested in the tails, versus the maximum likelihood approach that is going to require us to create a likelihood function that's going to be the product of our joint distributions given the parameters of interest. And what was nice about that is that we were going to maximize the likelihood that this observed set is the one that comes along. We're going to, in a sense, we're going to maximize, we're going to select parameters that make this observed set be the most likely observed set. And that's fine, so long as, again, you have a representative data set. But if you have one that doesn't have the kind of information that you're looking for, say out in the tails, oftentimes the extremes, then this may not be a great fit either. So both of them have their advantages. The method of moments is very much body-centric in its view. Maximum likelihood is more neutral to both the body and the tail because it does a little bit better job, but it's got some complications and it creates an optimization problem that can be unwieldy to deal with. And one that we didn't talk about, only alluded to, was the Bayesian approach. Which really looks at what the conditional distribution is, say, of the parameters given all our xi values. So now we've turned this around compared to what we had before, and that's going to be equal to, well, the joint of all of those, right? So all the xi and theta divided by our conditioning event, and we have to talk about what that joint is. This is now a joint distribution here in both cases. Well, joint of the xi's, you could say it's the marginal of this, just that random data set, no longer with the theta involved. Key thing here is that theta is our parameter, and it is a random variable. That's a key item in all of these that we're looking at. Those are random variables. Okay, so we're not going to really do much with this. You should just know and see how there is this idea of extending the Bayesian idea, that it exists out there, and in the instance that you come across this in practice, you'll have some idea that such a thing does exist, and you'll have a beginning point of where to go look at that. We'll focus on just these two, so I just only bring it up for completeness' sake. All right, and then the last thing here as a summary, before we head off into our confidence intervals for doing parameter estimation is the idea that we introduced here, the distribution of our sample statistic. And we said in a more shorthand way the sampling distribution, but it's a shorthand way of saying it, essentially the same kind of thing here. And we talked about an unbiased estimator. For example, the mean of x bar was equal to the mean of the property itself. We talked about how the expected value, the mean of the sample variance, was equal to the underlying population variance, so long as we used the n-1 portion or version of that, right? That was kind of key in that. And then we also talked about the central limit theorem and its role in how it gave us the probability distribution of x bar. We didn't really talk about that in terms of the variance. We will later. We introduced also the concept of standard error, and we threw down a definition of the mean squared error. We didn't really talk anything about it at all, explain anything about it, and partly because, in my view, these things get to be very confusing if you just talk about them in theory. You really need to have the actual data that you're working with in the context that you're trying to deal with it to really get a handle on that. And you might even say that, gee, wait a minute, everything you just did, Dr. Schmucker, feels that way. It feels very dry and disconnected. I get that. That's why I don't want to introduce any more, and why we're going to head off into confidence intervals and get our hands on some real problems, along with you'll have some homework that will go along with these particular examples of the method of moments and maximum likelihood. So let's cut that sort of theory, in a sense, to a close, and we'll get back into some detailed kinds of things in the next module.